Hey, good morning, everyone. So, introduce myself, Duncan Ellis. Recently joined Wave to Wave, who some of you may remember. I think we presented a couple of shows ago at Manchester, a couple of meetings ago. We're back today, and we've actually brought one of our devices along. I think some people were a little disappointed they didn't get to see it last time. So I said I joined the company fairly recently. One of the things that attracted me was this concept of bringing robotics into the network. So I had this vision that it was going to be really cool, and that's what I was hoping for. In reality, what we actually get is something that may not look quite as funky, but is a very elegant solution to a problem that we've been facing since the beginning of optic fibre networks, which in some cases we've almost forgotten about because we've had to work around it for so long. So what is this device? It is a robotic patch panel. It's low loss, low latency, all optical cross-connect. So we don't go through any OEO, we don't have any active components in the data path, so we don't worry about power loss or anything like that. We have two models that can manage either 256 fibres or 512 fibres within 11U. So 10U for the main switching matrix and 1U for the controller. It maintains a full configuration database, so we know what connections have been made, when they were made, who made them, and likewise when they were disconnected. We can handle single mode, we can handle multi-mode, doesn't matter. So whether your environment is more on the client side, more on the wide area network side, or even if you're deploying single mode within a data center, we handle it all. It's very low power. In its static mode, when it's just a logical control unit running, that's less than 55 watts. When it's in full active mode and we actually have a robotic arms moving, we got to a staggering 120 watts. So very low power, no major contributions to heat or power drain. And because it's all optical, we support any optical protocol, be it storage, be it IP, be it Ethernet packets, be it video, doesn't matter. Anything that can be transmitted on a fibre we can support at any speed. So again, you're not tying into a technology or a particular line rate like you would be with an OEO solution. So whether you're running 10 gig today, you're migrating to 100 gig, or you're looking at the new 400 gig Ethernet standards, doesn't matter. This supports all of it. So how does it work? A number of people over the years have tried to address this problem with forms of robotic patching. And one of the biggest challenges has always been to stop the cables tangling. You know, we've all seen the patch panels that are just a rat's nest of fibre or rat's nest of RJ45 cables, whatever it is. This is a very elegant solution to the problem. And what we do is we have a number of connectors. So we've got, is that the laser? No, all right. So going on the x-axis, we have the female connectors. So they just move from left to right or right to left. And then underneath the matrix, along the top, we have the male connectors, which move in the y-axis. So when we make a connection, the robotic arms pick up the connectors, move them out, and they physically link together and are locked together to make that physical connection. So whereas we traditionally think in a patch panel of taking a fibre and connecting it from one port to another, here we're effectively bringing the fibres together and joining them in the middle of the matrix. And this allows us to do that secure physical connection that gives us the low loss, low latency, and the ability to survive power failures. And depending how we configure it, we can do it east to west connections, simplex, duplex, or we can even configure it into an any-to-any connection so that a single port can connect to any other port that's on the same matrix. Now, 512 is not a bad number of fibres to start with, but certainly when we start to move into data center environments, we quite often want to go beyond that. So we can start to build cross configurations, whether it's 2-stage or 3-stage, to extend the number of ports that we can address. So what is the problem that we're trying to address? So we have all grown up thinking of the physical network as being static, immutable, unchangeable. If we do want to change it, it's an engineer going to site. It's somebody trying to find the right cable, pull out the right patch lead, reconnect the new one. It's slow, it's laborious, it's open to human error, and it's open to security issues because you have to let someone into the cage to do it. In this sort of environment, we're looking at a test lab here. You can spend days setting up a configuration to run a particular test environment. When you finish that and you need to move to the next environment, again, somebody's got to come in, tear it all down, rebuild a new test environment. It's slow, it's laborious, it's time and money consuming. If we think more about carrier networks, going into points of presence, you've got that connectivity from the transport equipment or the layer 2, layer 3 equipment connecting back to the physical fibre. Today we use distribution frames, IDFs, ODFs, to manage that connectivity. But it's all manual, it's all static until a human intervenes and changes it. And especially in the data centers. Today we are moving more and more towards this on-demand environment where people want to change configurations, even have self-service capability so that they can control their own resources, even if it's in a remote data center. It all works beautifully until we come down to the physical layer. Somebody has to go and patch that panel and change that configuration. So how does a robotic patch panel work? So what I've tried to do is put together a brief demonstration of logging into the system. We're running the standard CLI here, but we have SNMP. We also have a number of interfaces into higher level software packages, whether SDN controllers or NMSs. But on the standard CLI, we can type in, we use tabs to complete the command, use question marks to see what the options available are. So here we're having a look at the connection, have a look at show, see what the status of the device is. So I want to see what connections are made. So I'll do connection show connected, and in a second I can see every connection that's been made, the physical ports, the time it was made, who it was instigated by, and the logical port connections. I want to set up a new connection. I tell it which command to make, and we can now see the robotic arms actually moving. Now, the videos are slightly out of sync. I apologise for that, but it gives you a fairly clear idea, I think. So the robotic arms go and pick up the connector, picks up the female connector on the top, male connector is underneath. So it moves along its relevant axis to the intersection point. The female is inserted first, and that physically latches onto the metal matrix. So it physically hooks in, so it can't be moved. Once that's there, the male connector does a little seek underneath to precisely align the ferrules so that they're exact before that, as you can see, goes in, inserts into the female. Again, that physically latches to the matrix. So once that is made, the robotic arms move away, and that is fixed until somebody goes in and changes that configuration. So if there's a power failure, all the connections carry on working. If there's a power failure in the middle of a move, there's a full self-recovery program, and it will go in and it will find out where the arms are, repark, and then it's ready to continue any requests that you send to it. So by bringing this level of automation into the physical network, it allows us to address some of these challenges. So in the lab environment, you can connect all of your test devices, your resources, everything into this type of dynamic layer 1. So now instead of spending a day, 2 days, whatever it is, to reconfigure your lab environment for specific test, we can do it by running a script, and you know that the configuration is going to be put in correctly. There's not going to be any twisted fibers, transmit connected to transmit or anything like that. And we can accelerate that testing process, or the amount of demonstrations or test procedures going through a lab, by quite a number of orders of magnitude. In fact, we have some customers that have some significant lab investments who tell us that they are saving millions of dollars a year by being able to put a significant amount of tests through. If we go into a carrier environment, again, being able to select reports, change reports, a good example is bandwidth on demand. If I am offering a bandwidth on demand service, I either have to plug the customer into a high capacity port all the time and then just restrict his access to the bandwidth, but that costs quite a considerable amount of money in terms of high capacity ports, or I can repatch him on demand and have that true on-demand service and on-demand capability. And if we move into the data center environment, as mentioned earlier, we can build these cross architectures, so we can now build a true any-to-any fabric within the data center at the physical layer. So now I can do it more cost effectively. I can allow any resource to access any other resource. And in the world of on-demand capabilities, of people accessing cloud services within a data center, they can be changing the amount of resource they use, the cloud provider they're using. This level of automation, this level of flexibility completes that whole dynamic environment. So like anyone, we can talk about lots of advantages that it brings you. I think the thing that really stands out for me is the elegant cable management, the way that we can manage all of these fibers with no snags, with no catches. It's a fluid environment. But any of these advantages, what it drives us to is a more efficient use of our network resources. We've spent many years automating at every network layer except the physical layer. And we know the lower you can do anything in the network, the more cost effective it is. So if we can actually modify the physical layer, make it that virtualized resource that can be changed, adapted, make it more responsive, we are getting the best response for the dollar that we can do. So it's a very short introduction. As I said, we do have a roam out in the demo area. Some of you have been to have a look at it already. I would encourage, whether you're just interested in robotics and on what it can do, or whether you see applications in your own field, please come and talk to us. We'll happily show you a demo and explain a few more details. But with that, I'm very happy to take any questions now or afterwards.
James Blessing, just on behalf of Marek, who's remote, he'd like to know, can it do a TX-RX swap?
Can it do a TX-RX swap? Not directly, but the point is, when you put one of these devices into the network and you've configured it, all you're doing is doing the patching. So your TX-RX will already be set up. You're not changing any of that outside architecture, you're just doing the cross-connect. So there's not normally the requirement to do that.
Okay, and the second question was, how does it handle dirt?
Okay, great question. So, first of all, the device is put together in a clean environment. Everything is sealed within the unit. One of the things that we do is the female connector goes on top, so that any dirt is not going to go up and inside the female connector. What we find is, because the robotics are very precise, and do that last-minute alignment, the main source of contamination in patching is when you push dirt in. Because this is very closely aligned, the amount of contamination is significantly lower than you'd experience in a normal manual patch panel.
So the next question is, what is the dB loss you expect?
Sorry?
What are the dB loss you expect on normal circuit?
Sorry, I can't...
What are the dB, the decibel loss?
Oh, dBs.
Yeah.
So the typical loss, dB loss going through here is less than half a dB. So it's the same as or less than you'd experience on a manual patch panel. Because we have very high tolerances that we manufacture to, we're able to keep it down to an absolute minimum. So half a dB is pretty much the maximum that you'll ever experience.
Hi, Tom Elliott, Gyron. Oh. How many insertions is it rated for? How many times can we reconfigure the thing? without...
So, absolutely, it is a physical device. So the robotics are designed to withstand millions of changes. Each individual connector is tested to over 1,000 insertions per connector. And you think over the lifetime of a patch panel, 1,000 insertions is a lot of changes. The expectation is that it will endure more than that, but that's what we've tested to.
Does it do IPv6? the management interface, that is.
Sorry, even?
The management interface, that is.
Good question. I don't know that one. If you want, please check me afterwards and I will have the answer for you, but off the top of my head, I don't know.
So if I break a fibre, I've got £2 and 5 minutes to replace it. If a fibre in that breaks, how long does it take to repatch the entire robotic unit, and how long's the downtime of everything else connected to it?
Okay, so first of all, because it's robotics and it's not being subjected to manual handling by a human, the chances of a breakage are reduced. However, we don't rest on our laurels. What we've done is when we've built the matrix, we put spare capacity in. So we provide 128 fibres on each side of a matrix, but we actually have additional fibres that are there and available, and it's just a logical change of a logical assignment, so we use a spare fibre. So we have spare capacity that will survive. We can cope with those up to 4 or 5 fibre breaks per matrix side. Okay. Well, thank you very much for your attention. As I said, we are just outside, so on the next coffee break or at lunchtime, if any of you would like to come over and have a chat, we'd be delighted to talk to you. Thank you.
Thank you, Duncan. Thank you.